two kids home, but I'm just kind of hanging out, listening to some music, and it's really quiet.
It's been Hey, everybody.
Hi.
Well, somebody sounds like
Hello.
hey, Zanisha. Somebody sounded like they had a sore throat out there.
Yeah, my voice is just, oh my gosh, it's getting on my nerves.
Oh, do you feel as bad as you sound?
Yes, I'm a little stuffy.
I'm sorry.
It's okay.
Well, if you just want to, I understand if you don't want to talk as much, kind of, even though I enjoy your input, but I know it's no fun trying to talk a lot when your throat hurts.
It's okay.
Well, thank you. Let's see. We did the addition rule, and which included ones that were for mutually exclusive events that could not occur at the same time, and non-mutually exclusive events which could occur at the same time. And we've done a lot of the just empirical probability from data. And now I'd like to move to the multiplication rule. And we're going to end up working quite a few problems before we're done with this module. There's only 5 real mathy modules, and this is the third one. So we're in a really good spot. So I feel like let's just cover it really well. And we're going to do, I have some of the practice problems today, and then we'll move on to working the homework assignments. Now, the practice problems are just practice. But when we work through the homework assignments, those are for a grade, even though we'll kind of do them in class together. So make sure the homework assignments are the ones you get down the answers for, and you're careful when you take them so you get decent grades on them. Let me define some things first. I got toolbars everywhere here. Overarching vocabulary is the multiplication rule, but there's going to be some definitions under there before we actually write out the rule. Two events are we're talking about 2 events now. The addition rule, we were mostly drawing 2 cards. What's the probability? So there was 2 events, but it was drawing 1 card followed by another. No, we were drawing 1 card. Sorry, we were drawing 1 card. What's the probability of drawing a king? First of all, and then it was drawing 1 card. What's the probability of that 1 card being a ace or a king? These are going to be like drawing 2 or more cards. What's the probability of drawing ace and then a king? That kind of thing, 2 consecutive cards. 2 events are independent. Let me give them names. That's always a good idea. Two events, A and B, are independent and one event I could even say the first, when the, and a lot of these definitions, when you see it in practice, the definition will be clear. When first event occurring does not change the probability of the second event occurring, does not affect or effect. I think it's affect. And I'll show you a little example. So for my events A and B, let's talk about a regular old die, the old six-sided die. Well, wait till I get to, I'm getting ahead of myself anyway. Let's get them both defined, and then we'll write the rule. And okay, two events. You probably can tell just what the definition of this one's going to be, just from the first one. Two events, A and B, are dependent defining dependent events as opposed to independent events when first event occurring does in fact affect the second one. So does not on the first one and does on the second one. All this writing for that. Does affect. All right. So there's the definition of two events that are independent and two events that are dependent. And for the first one, the rule of the probability rule is the probability of A followed by and B occurring is simply the probability of A times the probability of B. So that's why we call it the multiplication rule. So when you're reading, when the question, like they always are, is just words, they'll say, you'll notice the difference between this and the addition rule, because the addition rule would say, what's the probability of drawing an ace or a king? Well, you're only drawing one card in that problem, and you're asking yourself whether that card is an ace or a king. When you see that or, it really tips you off that you're using the addition rule. Here you'd say, what's the probability of drawing an ace and then a king? So you're drawing two cards consecutively. And then, well, what's the probability that you draw an ace out and then the next card is a king? Now, if they're dependent, meaning the first one affected the second one, and the problem I just told you is probably a dependent one. And we'll see why. The probability of A and B occurring when they're dependent events, you'll see it clearly here in a second, is the probability of A occurring times, and here's some new notation here, the probability of B occurring given, that's just a little vertical line, A has already occurred. So this notation is B given A. So you have some prior knowledge. A has already occurred and that affected B. So you know that. So that's why we write this way. B given A has occurred. Let's explore that a little bit more. Now, I might be misspelling occurred all over the place here, and I apologize. For some reason, double letter words is always, I can't remember where to put a double letter and where not to. Some sort of problem I've always had. So excuse me if I'm misspelling occurred or occurring. Probably am. But anyway, suppose the problem asked, what's the probability of drawing an ace and then a king, drawing an ace followed by a king. All right, what is the probability? I'm gonna write it down here. Probability of ace and king. Abbreviating a little bit. I know it's painful watching me write painfully slow, but this surface is a little goofy. And I have a new one, but then the guy dropped it off at the house, and after he left, I started to test the whiteboard out, and the stylus was like spider webbing. Every time I would write, all these little lines would go off of. So I need to get him to look at it again. So sorry, I haven't resolved that yet. But anyway, what's the probability? All this talk. what's the probability of this first part? What's the probability of drawing an ace out of a deck of cards? How many aces are there in a deck of cards?
4.
Or
4. Glad to hear you. I didn't put you to sleep. I talked for a long time. So that's 4 out of 52, right?
yes.
Are we good?
Yes.
Good. Now, the second part of that, you've taken an ace out of the deck. You've drawn an ace. The second part is how many, what's the probability of drawing a king? Well, how many, you've taken an ace out of the deck. How many kings are in the deck?
4.
Still 4. Very good. But how many cards are in the deck? So Lexi, oh, go ahead.
52.
Well,
Or are you saying now that they're gone?
I think that's what I'm saying. You drew that first card out and it was an ace and you have that in your hand.
Yeah.
Now here comes the second event. You're going to draw a king. So there are 4 kings in the deck, but how many total cards are left in the deck if you have 1 in your hand?
48.
No, you only have 1. You only
Oh,
do-
if I only have 1, 51 then.
right.
I thought you're sorry.
No,
I
that's
thought
good.
I was doing the 4.
No, that's fine. Don't apologize. We're just now learning this for the first time. Very good. So can you see, I think this makes it a little clearer how these are dependent events, because drawing that first card out of the deck reduces the size of the deck. Because if the question just simply asked, what's the probability of drawing a king? It would be 4 out of 52. But something happened first. You have prior knowledge that something has already occurred. And that was you took a card out of the deck. So the deck got smaller by 1 card. Does that make sense?
Yes.
Okay. And we'll do a lot more of these. If this is the first time you are seeing this, so I don't expect complete understanding right at the get-go. If that was the case, we could probably teach the whole class in a week.
Hmm.
But we
So-
learn these things. Go ahead.
So this is a dependent example?
Yes. Now, an independent example. Suppose I was rolling. I should have left myself a little bit of room up here. So here's an example here. Roll. I'm going to have to abbreviate a little bit. Probability of rolling a die rolling a 3 and then a 6. Well, what's the probability of, let's see here, I'll say 3 and followed by a 6. What's the probability if just a standard die of rolling a 3?
1.
1.
6.
What was that, Mallory?
1/6.
Yep, there's 1 3, or who was that? I couldn't see the name.
Jalen.
Jalen, sorry. All right. So Jalen says 1/6 because there's 1 3 on a die. Oops, what am I writing that there for? There's 1 3 on a die and there's 6 sides on the die. So that's 100% correct. Now you're going to roll that die again. What's the probability of rolling a 6?
The same thing, right?
Yeah. So that is it. So just because Jalen rolled the die once and got a 3, that did not change the probability of her rolling the die again and getting a 6, right? The first event occurring did not affect the probability of the second event. Just because you rolled a die once doesn't change any of the probabilities when you rolled a second time. Down here with the cards, you've reduced the size of the deck. So can you see the difference?
Yes.
It really happens in the sample size. It really happens, the difference happens, well, sometimes the numerator and the denominator, but it definitely happens in the denominator. You're rolling a die. Every time you roll it, that's an independent event. It's like flipping a coin. Just because I flipped a coin and got ahead does not change that coin anyway when I flip it again. You know, that my probabilities are still 50-50. Now, as I deal out cards, the deck keeps getting smaller and smaller, so the probabilities keep changing. So when the first event occurring affects the second event, the probability of the second event, those are dependent. The second one depends on the first. When the probability doesn't affect it, those are independent. The probability of the second one is not affected by the first one. Now, what math textbooks will do to get around and get more examples by using a deck of cards, they'll say, what's the probability of drawing an ace and a king with replacement? Meaning I draw a card from the deck of cards, I note that it's an ace, but then I stick it back in the deck. We shuffle it, then we draw a king. So the deck would be the same size, would be 52. You know, that's kind of an awkward way, I think, to do independent events, because there's very few card games where you look at your cards and put them back in the deck. I guess card tricks do that sometimes. But you'll see that a lot and we might see it when we go through some of the problems. They'll say with and without replacement for cards. If they say without replacement, that means Jalen drew a ace, held it in her hand, then drew a king. So the deck did get smaller. If they say with replacement, it would be she drew an ace, noted that it was an ace, put it back in the deck, it shuffled it, and then drew for a king. So it's a little awkward, but you'll see that quite a bit. But just remember the definitions. If the first event occurring does not affect the probability of the second, then they're independent. If it does affect it, then they're dependent. Because before all this is done, we're going to do some funny stuff with this. This probability of B given A has already occurred. And I may have talked a little bit about the lie detector problem. And that's good because that's called conditional probability. And we'll get to that. And I struggled with that when I was in your seat in my first statistics course when we went over conditional probability. So I'm very deliberate about doing it now. You know, I follow steps carefully and everything because it's not as intuitive as some of these other things, but it leads to really important results. But the results are not always what we would intuitively think they are. Like I said, when you take a lie detector test, suppose I'm the police and somebody's been murdered and I suspect Lexi's the one who did it.
Oh.
She looks guilty. So she could be, when I bring her in, she could actually be one of four things. When we talk about conditional probability, she could be telling the truth, given that she's guilty. So she would come, I would bring her in and she would admit to it right away. I murdered that person and she was guilty and she did murder that person. She could lie given she's guilty. That is, she did murder that person, but when I put her in the lie detector test, she told me she did not. She could tell the truth given she's innocent. So I brought her in and she had nothing to do with it. And that's what she tells me. Look, I didn't do it. And then the fourth one is she could lie given that she's innocent. She could say she did it, even though she didn't. Which that happens if you ever watch those crime shows. That happens more than you would think. People think, why in the world would somebody say something where they confess to a murder if they did not do it? Well, after you see the grilling some of these people get in interrogations, and sometimes their limited reasoning capacity, they can really get bullied into doing that because they get exhausted and things like that. So it's interesting. It opens a wide array of possibilities. And when we get to that, we'll watch a little video about that related to lie detectors. But it's also the same kind of things used in your spam detector in your email. What's the probability of Google taking an email that's not spam and, well, putting it in a spam folder, given it's not spam? There's actually 4 different things for that too. Sometimes they sort them correctly. It is spam, it goes into spam filter. It's not spam, it doesn't go in the spam filter. But then sometimes they organize them and it's not spam and it goes into spam filter anyway. Or it goes into my inbox and it is spam. There's a chance of those things happen. So it becomes a much more complex problem, but we'll get to that. And I probably talked more than I needed to there. But I think the best way to kind of learn to do this is to work some problems. So I think that's what we'll do next. Does everybody have what they need off the screen?
Yes.
And I'm not accusing you of murder, Lexi,
Oh, good. I was worried.
just so you know. Yeah. Let's see. You probably weren't too worried though.
Nope.
Let's see here, Brenton, scroll down and we'll go back through that classroom practice. What did I call it? Class practice here. And we skipped over some problems and now we should have the tools we need to do them. All right, card is drawn, find the probability. Okay, so we did this one already, and this was an addition rule problem. And you kind of know that you kind of get tipped off to that because of this. It's an OR problem. Hold on one second here. All right, so we already did that one. Let us check number 2 here. Where my little find the probability or a heart. We don't need to do that one. We did that already. Or a black card. Got it. This one is a conditional probability. So I'm going to kick that one down the road and do all the simple multiplication rule problems first. So we'll get back to that one. Don't worry. Now this one becomes an and problem because you're taking a multiple choice test. Each has 5 questions. No, you're taking a multiple choice test that has 5 questions. So now we've got 5 events. You're taking 5 questions. Each question has 5 choices. So it's similar to these. Our questions here have 4 choices, but imagine yours had 5. Only one of the choices is correct. You randomly guess at the answer to each question. What is the probability that you answer the first 2 questions correctly? So even though sometimes these problems are awkwardly worded, there's 5 questions, but all they're interested in is the first 2. So we're really just you're guessing at problems. You're guessing at these first 2 questions, and you're asking what's the probability of getting them right. This means I'm looking for the probability of getting question 1 correct, followed by, these are good questions to do for those students who think it's a good idea to guess on tests. You'll see how slim your chances really are. I forgot to write the number in there. The first question correct. And followed by the second one correct. So that becomes an and problem where it's 2 consecutive events. You're answering the first question, you're answering the second. This 5 question business right here is just noise. That doesn't even play into the problem. I know that makes it a little more difficult. This is just a practice problem. Because really what they're asking for, the probability of the first 2 questions. So this becomes an and problem. Now, if you're just guessing on a test and you guess on the first question, does that change your probability to get the second one correct at all? Are those independent or dependent events?
Wait, can you say it again? It went out on my computer.
Okay, if you're guessing, all right, sorry, hold on 1 second here. The doctor's calling me. Sorry about that. I'm gonna mute for a second. Sorry about that. Okay. So let's do this one. Or did I get the answer to that question I asked before that call? Is when you guess on the first question, does that change the probability of whether you can guess on the second one and get it right? Does that help you at all or hurt you at all?
I guess if you get the first one right.
But then how does that change when you guess on the second one, how does that change the probability of getting the second one right?
I guess it doesn't.
No, in this case, you have to look at them as two separate events. You're guessing on two. You get the first one right, that makes you feel good, but you're still guessing on the second one. And you haven't reduced the number of choices. You haven't increased your guessing ability. Nothing's changed. So you're just flat out guessing again. It's like flipping again. So it does not. So what's the probability if there are, here's about this, there's 5 choices for each answer. What's the probability that you guess on the first question and get it correct? If there's one correct answer, 5 total choices, what's the probability of getting it correct? Blind
One over-
guessing.
1
One
over 5.
Yep, very good. Jalen, 1 over 5. One correct answer out of the 5 that's given. Now, the second one, we've established that these are independent events. So it's a multitude, and it's an and problem, even though it didn't read exactly like that. But you're doing answering one question and then answering another one. What's the probability of getting the second one correct? The
The
first
same.
one, yeah. Sorry, I talk too much sometimes. Also 1 over 5. So what is the probability if you're like, I'm going to take this 2-question test, and I'm just going to guess on both of them, and I bet I get 100. What is the probability that that actually happens? 1 times 1 is 1.
Is it 0.2?
Well, it's 1 over 25. What does that turn out to be?
Oh, 0.04.
Is it? Okay. I couldn't do that fraction right away. Okay, 0.04. So that's a 4% chance. So if your plan is to go in and guess and get a perfect score, you have a 4% chance of doing that with only 2 questions. So that's not a good strategy at all. Not a good strategy. All righty. I can tell it's hunting season because I live in the country and I can hear guns going off. I kind of like it. Fall is here and people are out hunting.
Best.
Do any of y'all hunt?
I don't, but my brother does.
Yeah. Yeah, I don't hunt really at all either. Though I like that other people enjoy it so much. You know, I like
Mallory
people enjoy their. What's
I-
that?
I hunt a lot because of my siblings, and they're all boys. So
Yeah, and you were the little sister, so you had to do it.
yeah,
I know. I like when people have like hobbies or little things they do that they really enjoy. It's neat to see. So I like. I live in Palmer. Everybody hunts around here, and I just started to hunt some last year, but I probably won't get out this year with a friend because I got enough land here. I think I could enjoy it, but I just never got around to it before. But anyway, I like to hear the shotguns go off and the rifles go off in the fall.
I think it's cool, but I know I could not ever do it myself.
Yeah, it's not.
But I
for-
respect it.
Right. That's a lot of that stuff. I'm like that way. You know, I maybe not do. It's not something I enjoy, but I respect other people's
Yeah.
right to enjoy it, and I like that they do it and enjoy it.
Yeah.
So, all right, let's see. This one we did before. That one I'm going to skip because really the same question we just did. So it's kind of a duplicate question, just worded differently. All right, well, here's a similar question, but now there are two true and false questions. I'm gonna guess on two true and false questions. What's the probability of answering them both correctly? Well, if you're guessing on a true and false question, what is the probability that you guess and get it correct?
1/2.
What? Yeah.
Yeah, because now the sample space is, there's only two in the sample space, right? A true and a false. So only two possibilities. One of them is correct. So I have a 50-50. I have a 1/2 probability of getting it correct. Now, here again, these are independent events. I'm guessing again on the second question. It's true and false as well. What's the probability I get the second one correct?
1/2.
Yeah. So guessing on two questions on a true and false test, the probability of getting them both correct is what?
It's 0.25. Oh, it first to be 1/4.
Yeah.
And
And
then
that is 0.25. So your chances of guessing and getting them correct go way up when there's only two choices as opposed to five. On that last one, you were guessing on two questions, but they each had five choices. And our probability at the end was 4%. Now it's 25%. So we could guess at two true and false questions, and it would be reasonable to think we could get them both correct. That could happen. Still better to study. My experience over these many years is that's really a boy thing to do. Plan on going in and guessing, that's the boy strategy. The girls in my class all these years have been so much more studious. I shouldn't say that, but just anecdotally looking at it over the years, better students, better math students, and more studious and more conscientious and all those things that make you successful at math, which is funny to me because I'm old enough to remember when girls were told that they're not good at math, and they're not, boys are good in math. Well, boys can be good in math, but my real teaching experience shows me that the female students I have been better. So
oh, look at us.
that may have been sexist to say that. I don't know. So I apologize, but it's just,
Hey, if that's sexist, I accept it.
that's okay, right? But that wasn't just pulling that out of the air. I really have noticed that over the years. And I've taught for the last 6 or 8 years the STEM students in the governor's school, which are the really gifted students in math and science and things like that, seniors in a STEM program. So that's where you're getting, and they come from multiple counties. So it's some of the best students you get in a fairly large area. And they go into things, they graduate and go into engineering and computer science, things I wouldn't have probably, more difficult things than I did. And I really have had the female students have been better overall. Just that. Maybe I don't have a big enough sample size and that doesn't mean anything. That's just my observation, we'll call it. So any female students out there, don't ever let anybody tell you that you're not good in math because you're female, because I don't believe that. And I have a son too. So I have 2 girls, but I do have a boy. And he was smart, but sometimes it was hard to motivate him. Anyway, we did that one.
I think we stopped at 17.
Yeah, there was some mixed in though. I just want to make sure.
Did we do number 8?
No.
I didn't think so.
He said that one was similar
Yeah.
to the one that we did.
Yeah.
Okay.
Well, just to show you where that one says the probability of answering 2 multiple choice questions if they each have 5 choices. So that's the question again, 1/5 times 1/5. Yeah, the last one we did, or the one before that, said there were 5 questions, but only asked us about the first 2. So essentially, it's the same question. That's why I skipped it.
For our last Zoom meeting, I have an answer for question 11, 12, 13, 14, 15, 16, and 17.
Okay.
So
Yeah, I think we can just browse down through these and get them fairly quickly here. So let's see. True and false. Get back to where I was. You said 11. On an ace, okay. Drawing a red card, we did that one. Drawing a heart, well, maybe there's not many of these at all, which is probably good because we do have another class after that. Maybe that's all like that, and I have to go to the next group, which I may wait till the next class to do, because that leads us into conditional probability. And I like that to be a full class because there's a lot to talk about when it comes to that. Here we go. Here's one for us to do. You are dealt 2 cards successfully. So dealt 1 card and then another one from a standard deck of 52 cards. Find the probability that the first card is a 2 and the second card is a 10. Oh, and without replacement. See that I told you were going to see that in some of these questions. So that means you draw the first card, you hold it in your hand. Then you draw the second one. Are those independent or dependent events?
dependent.
Very good, because the deck gets smaller, doesn't it?
Yes.
Very, very good. That's the key. All right, so the probability of a 2 and then a 10, of a 2 and then a 10. So what is the probability that you draw a 2 out of a deck of cards? How many 2s are there?
Four? Is it
Very
four?
good. Yeah. 4 2s in a deck of cards. How many total cards in that deck?
52.
52.
Very good. All right, now you drew a 4 out of the deck, excuse me, a 2 out of the deck. And they want to know, what's the probability that I draw a 10? So you have a 2 in your hand. How many 10s are in the deck that's left over?
It'd be 4 over 51, right?
Hey, very good. That's exactly what it would be. Nice. So I'm going to need somebody to multiply those together and tell me what the probability is. So the
Wait,
fact that they were dependent is right here, because we drew a 2 out, but we didn't replace it. We held it in our hand. So then when we were going to draw a 10, the deck was 1 card smaller. There were still 4 10s in the deck, but there was 1 fewer card overall.
So are there 4 10s in a deck of cards?
Yeah, there's 4 of each.
Oh, okay. When I looked it up, I didn't see that.
Yeah. Well, there's 4 of each card, 4 aces,
Oh,
4
yeah.
kings, 4 queens, all the way down. Sometimes it's better to have that little graphic up of what a deck of cards looks like when you're doing these, because especially if you're not familiar with playing cards. And a lot of these statistics book were, the people that write these books were very familiar with card games, and that's not really y'all's thing. And I get that, playing the old people card games. So, but anyway, can somebody do that multiplication for me?
Yeah, I got it. It was 4 over 26, 2,652.
It'd be 16 over that, right?
Oh, sorry. Yeah, 16. Sorry, I was looking at 4. I literally wrote 16 down.
Okay, over 2652.
Yeah.
And how does that come out as a decimal if you divide 16 by 2652?
0.0060.
There we go. So not a very good, I mean, that's less than 1%.
Yeah.
So if you're drawing 2 cards and you need, in poker, if there's 2 cards to come and you need a 2 and a 10, you're in big trouble. You're in big trouble. I hope you didn't bet the farm. All right, so there's a good example. And let's see, we'll finish this up. How many different codes are possible? Oh, that's a counting rule. I think I need to save that too, so we'll do that. That's a fun thing to do too. And that's a counting rule. All right, so I think we'll wrap it up for the day. And on Wednesday, I'll show you that counting principle. And then we'll talk about conditional probability and answer the other questions on this practice. And then we'll get to the, what's that?
Oh, sorry. So 4 and 5 are the conditional probability questions, right?
I'm not sure, whatever ones I skipped.
Okay. Thank you.
Usually with the conditional probabilities, the key word is given. You know, we had, when we wrote that definition down or the equation down, it was B given already, A had already happened. And here it is right here. What's the probability that she owns a credit card given that the student is a freshman? That's kind of a tip off that it's a conditional probability, but we'll do that next class. However many questions there are on here, because then we have the homework assignments to do. So there'll be some more coming down the road. But anyway, thanks everybody for coming today. And if you need me between now and Wednesday, just text me. I get texts from students often, and I try to get back to them quickly and take care of what they need. And I enjoy hearing from you. So just let me know if you need me. Otherwise, I'll see you on Wednesday.
Thank
Thank
you.
you.
Okay,
Bye.
take care.
All right. I hope you feel better, Anna.
Mr. Ritchie,
Yes.
it's Mallory again.
Yes, ma'am.
This Wednesday is the only day I could get a hair appointment. So I'll be on Zoom, but I might just be really quiet because I'll probably be there.
I thought you were going to tell me this Wednesday is the only day you could go hunting,
No, it's my hair.
which would be, hunting would be okay too. All right. That's fine, Mallory. I won't
I'm
call.
sorry about that.
That's no problem. That's no problem at all. I'll see you then. I just won't hear you.
Okay, thank you.
All right.
Have a good
Bye.
day.
You too.